decreased by half. So this is so this material is tough only for once. So, but in the application of hydrogels, in the soft robots and hard valve, so all these applications require for fatigue loading, right? So the hydrogel is not good enough. So when I was a PhD, we have initiated the study for the fatigue of hydrogel. So here we use the simple hydrogel polyacrylamide. This is the cyclic fatigue test, right? Here you cyclically stretch the hydrogel and you record the crack propagation length, and we get the crack propagation rate. So for the hydrogel, we have to maintain the humidity in the fatigue test. We get the crack growth behavior for the hydrogel, and we get the fatigue threshold for this kind of simple hydrogel. For the hydrogel, the fatigue threshold is different from rubber because there is a water molecule. The water molecules will change the polymer chain and the polymer chain length and the fracture surface of the crack, right? So the fatigue threshold of the hydrogel, the term of water content will come into the formula. This is the difference. Okay, after this study, many people start to study the fatigue of hydrogels. So how about the two famous hydrogel? The first one is the tough hydrogel. This hydrogel is called polyacrylamide and alternate. So this hydrogel has a very high toughness. The toughness is 1,000 joule per meter square, but the fatigue threshold is only 50. So there is 20 times difference, right? So how about the double natural hydrogel? As we saw in the video, this hydrogel is very tough, but its fatigue threshold is also very low. So this fact raises a lot of interest in the material scientists. So okay, so we idea came into our mind, right? Can we study the dynamic crossing hydrogel? What does this mean? So this hydrogel includes the disulfide bonds. So these disulfide bonds can break and reform under UV light. So you send the UV light, right? This covalent bond can break and they form again. So this process, right? This process can lead to stress relaxation. Why? Because the newly reformed polymer chain does not carry any stress. So the initially loaded stress is released. Here is the stress relaxation test. So if we send the UV light, you can see the stress decrease, right? This is the photoelastic test. We can also have this result. So in this video, we saw that if we do not send the UV light, the crack will propagate very fast in the hydrogel. If we send the UV light, right, the polymer chains will break and reform again to release the stress. So the stress concentration at the crack tip is reduced. So the hydrogel can resist this kind of crack greatly, right? So the toughness can be improved. The similar story is to the fatigue case. So you can see the fatigue threshold is increased from 20 joule per meter square to 200 joule per meter square. So this kind of material is dynamically covalent cross-linked and can heal a little bit, but we found its threshold is still lower than biological tissues. So next, we want to study the fatigue fracture of heart valve. So heart valve is very interesting. Our human being has, actually we have 4 heart valves in our human body. So the heart valve can flap over 3 billion times during one's lifetime. Okay, so this is very fatigue resistant soft tissues. But if unfortunately one people gets the heart valve disease, right, he has to do the open chest surgery to replace the heart valve. Every year there are many people, so millions of people die from this valvular disease. So they will replace the mechanical valve made of metal or biological valve made of the biological tissues. So, okay, from 2002, so the doctors invented the minimally invasive surgery. So they compress this heart valve into the vessel of small diameter, right? And use the get wire to get the heart valve to the location, right? To the location of heart here, right? Here, the heart valve functions. So in this heart valve, this heart valve is made of the soft leaflets and the expandable stent, and the leaflets are sutured on the stent, right? So in this kind of surgery, rigid materials are not adapted, right? So we want to study why this kind of soft tissue has so wonderful particle resistance. Okay, so what's this material? This material is bovine pericardium. So this is a core, and this is the core's heart, right? We harvest the very thin membrane from the bovine heart. So this is the membrane. The membrane is very thin. The thickness is around 300 microns, right? This is the material for commercial use of heart valve. This is the commercial use, okay? So this membrane, this is the microstructure for this membrane. Actually, it's made of collagen fiber and elastin fibers. So this is the collagen fiber is helical collagen fiber, right? So the diameter for collagen fiber is 30 microns, 30 microns. Okay, so because there are a lot of collagen fibers and the collagen fibers are aligned, the alignment of collagen fibers actually leads to the anisotropic properties of the bovine pericardium or BP membrane. So we have to know the fiber orientation in this soft membrane, right? So actually we have three kinds of orientation. So in this one, the fiber is perpendicular to the loading direction. In this one, the fiber is parallel to the loading direction. This one, the fibers are dispersely distributed, right? So we use the small angle laser scattering. So we sign a laser and to get the scattering pattern, and we analyze the pattern to know its alignment direction for the collagen fibers. Okay, so firstly, we study the fracture for this BP membrane. We found that the BP membrane, in the BP membrane, for the three cases, PD, SD, or SD, XD, so we found that the crack always deflect in the membrane. What's crack deflection? So here, the crack does not propagate horizontally. It deflects vertically or tilted, right? So we want to predict the crack propagation direction. So we calculate the G integral around the crack tip. In the finite element analysis, we can change the fiber orientation angle theta, and we can also change the crack propagation direction alpha. So we calculate the G integral. We find that at a specific propagation direction alpha, the G integral can reach a maximum, right? So when the maximum G integral reaches the toughness in this direction, the crack will propagate in that direction. And this fracture criterion can predict the propagation direction in the three cases of the tissues, the XD, PD, and SD. And as we see, the membrane is always sutured on the stent, so the suture retention behavior for this membrane is also important. So we use a suture thread to pull this membrane, right? For this kind of fiber direction, the crack will propagate horizontally. And for this one, when the loading direction is parallel to the fiber direction, the suture thread will cut the matrix, and you can see this is the cutting behavior. And these behaviors can be simulated by the finite analysis. So next, we want to study the fatigue fracture for this tissue. So we firstly observe the crack breathing behavior for this tissue. Actually, this BP membrane is quite tough. It's quite tough. It can resist the crack very well. You can see this is the crack bridging zone, and these are collagen fibers bridging the crack, and the initiation toughness for this tissue is very high. It's 20 kilojoule per meter square. And furthermore, the BP membrane is flow sensitive to the is flow insensitive to the crack. So if we use the DIC test to measure the strain concentration factor of these two materials, for the biological tissue, the BP, you can see the strain around the crack tip is very homogeneous. But for the synthetic rubber TPU, you can see the strain concentrates at the crack tip. This means the biological tissue is not sensitive to the lung crack. Okay, how about fatigue damage or fatigue crack? So we do the fatigue damage test. You can see the maximum stress will decrease and the residual deformation will emerge. The fiber orientations can change during the fatigue test. But this soft membrane, right? This biological soft membrane is quite fatigue resistant. If we cut the lung crack, do the fatigue test, you can see the fatigue crack cannot propagate a lot. It only induce a little bit of fiber pull out or fiber break at the crack tip. The fatigue threshold for this membrane is very high. It's 5,000 joule per meter square. It's 2 orders higher than the natural rubber. So the biological tissue is very good at fatigue resistance. So, okay, so now we want to know the BP is insensitive to the force under cyclic load. So here in this uniaxial tension test, we cut a small crack, 1 millimeter, right? So and we cyclic stretch this this sample after the 1 million cycles. After the 1 million cycles, the small crack does not propagate. It means the BP membrane is not sensitive to this to this flaw. And furthermore, we want to prepare the hard wall, right? So we use the suture thread to suture the BP leaflet on the stent. When we suture it, we will introduce the suture holes. The suture holes have diameters of about 100 microns. These suture holes can be viewed as initial flaws. So then we do the accelerated fatigue test. You can see, and we apply the pressure to do the fatigue test. So for the biological tissue, it can endure 200 million cycles. But for the TPU rubber, for this synthetic material, its fatigue life is very low. It's only 2 million cycles. You can see this BP membrane is very, very good. Very, very good. Okay, so why the BP membrane or biological tissue are flaw insensitive? It's because it has a structure of a strong fiber and a soft matrix. Here, collagen fiber, right? Collagen fiber is very strong, and the soft matrix, the soft matrix maintains contains the protein and the elastin, right? So in this specific composite structure, if you do the mechanical analysis, you can see the load transfer length around the crack tip is related to the modulus ratio between the soft matrix and the strong fiber. So a larger modulus ratio, a larger load transfer length. When you have a large load transfer length, the stress around the crack tip can be deconcentrated. That's why the soft tissue is flaw insensitive. Okay, so Now we know why the soft tissue, or the soft tissue, right, hard wall is fatigue resistant, and now we can develop the fatigue resistant hydrogels based on this mechanism, right? So actually, so in 2019, so Professor Xuanhe Zhao from MIT and Professor He Ximing from UCLA, they found that the PVA hydrogel, can mimic the biology tissues such as hard wall, bones, and muscles. The fatigue threshold is also very high. It's around 1,000 joule per meter square or 10,000 joule per meter squares. But this mechanism is limited to the PVA hydrogel. Later on, many groups are developing fatigue-resistant hydrogels using the strategy of soft composite or corrective softening strategy or nanofiber reorientation, right? So people are focusing on the fatigue-resistant hydrogels. So what do we do? So here, first we carried out a dimensional analysis. So for the homogeneous hydrogel, actually the polymer chain is the load-bearing element. If the crack propagates, it will cut the single polymer chain. The energy stored in the single polymer chain is actually very low. It's 10 to 100 joule per meter square. But if you use the macroscopic fiber to mimic the polymer chain, right? So in this case, the crack propagates by cutting the macroscopic fiber. So the diameter for this kind of fiber is around micrometers or millimeters, right? Or millimeters. So the energy stored in the fiber is very high. It's 100 to 10,000 or 1,000 joule per meter squares. So the fatigue threshold can be improved from 10 joule per meter square to 400 joule per meter squares. So this case, the softer composites have very high fatigue thresholds. So okay, so here in this paper, we want to use the soft composite strategy to prepare the fatigue-resistant hydrogels, mimicking the hard wall. Right here, we first we print a skeleton, right, and we immerse it into the solution to increase the modulus of the skeleton, and then we cast a matrix to get the composite hydrogel. Right. So here is the 3D printed hydrogel. This brown hydrogel actually is very stiff. It's used as the skeleton. So here, this photo is the composite hydrogel. The transparent part is the soft matrix. The brown part is the stiff hydrogel, right? So this composite hydrogel has much larger toughness than the matrix and the skeleton. Why? So if we look at the fracture behavior here, so this is the composite hydrogel here. This brown one is the stiff hydrogel. This transparent one is the soft matrix. So when the crack propagates, so the crack is firstly blunted, and after the fiber ruptures, the crack can propagate, right? You can see the stretch is much larger than the matrix and the skeleton. And furthermore, the fatigue threshold for this composite hydrogel is very high. It's around 500 joule per meter squares. This fatigue threshold is higher, much higher than tough hydrogel, right? So now we have this hydrogel and we have 3D printing technology. We can print hard wall. We get the CT images from the doctor, and we print this 3D hard wall. To test its fatigue property, we set up the hydrodynamic test system. Here, the video. So if you do not use soft composite, so the homogeneous wall, the fatigue property is very poor. After 500 cycles, you can see the crack occurs at the edge. So if you use the soft composite hydrogel, so the fatigue life is increased to 50,000 cycles. So after this paper is published, many people come to us to ask for collaboration. but we know the advantages and the disadvantages for this material. So the advantage is that the hardball is fully made of hydrogel, and it can have complex shape, and the fatigue threshold is high. But the disadvantage is that the cycle number is still very low. It's 10,000 orders of magnitude. It cannot satisfy the requirement. So the reason is here. So in the previous part, we use the hydrogel fiber, right? The hydrogel fiber, the strength is on the order of megapascal. So why don't we use the high strength fiber like the composites, right? We can use the glass fiber and the nylon fiber. For these fibers, the strength is very high. It's gigapascal, right? Okay, so if you use this high strength fiber, you have to consider more. So you have to consider the requirements for biological tissues. For the biological tissues, they have both low modulus and high fatigue threshold. Let's look at the heart valve, right? The heart valve here is the heart valve tissue, pericardium. This is the heart valve tissue. The modulus is very low. It's on the order of 1 megapascal. But for the fatigue threshold, it's very high. It's 1,000 joule per meter square, right? 1,000 joule per meter square. So why this heart valve has low modulus and high fatigue threshold? Because it contains a lot of crimped collagen fiber. So the fiber is crimped. At a small stretch, it's crimped, right? You stretch it, you stretch the fiber will become straight. And so the modulus is low at the small stretch. But after the fiber is straightened, so the fiber can resist the fatigue crack growth. Okay, so mimicking this structure, we develop a composite hydrogel. The hydrogel is made of PVA hydrogel and knitted nylon fiber. So this is the nylon fiber. This is the photo for the nylon fiber. This fiber has this knitted geometry, right? This geometry. And the hydrogel, right? Hydrogel is made of water. So the water can immerse or white the nylon fiber very well. The whiting behavior can ensure the good interface. This is the fiber, this is the matrix, right? So here is the fabrication process. So when you fabricate the hydrogel, we embed the nylon fiber inside the PVA hydrogel. And to make it more tough and fatigue resistant, we dry and anneal this PVA hydrogel. This is a very classical procedure for preparing the PVA hydrogel. So after drying, you can see this composite is very stiff, right? It can bear the load of the weight. And then we swell the hydrogel again in the water, and we get the equilibrated composite hydrogel, right? So the matrix is PVA hydrogel. The fiber is nylon fiber. So how about the interface? Actually, the PVA molecules can form the hydrogen bond with the nylon polymer chain, right? This is the hydrogen bond. We carry out the MD simulation to calculate the number of hydrogen bonds between the PVA polymer chain and the nylon polymer chain. You can see actually the drag and anneal process can actually increase the number of hydrogen bonds. Okay, the interface actually between the PVA hydrogel and the nylon fiber is very well. Let's look at the stress curve. So this red one is the stress curve of the biological tissue, heart valve tissue, right? And the blue one is the stress curve for the composite. So the strength is similar, and the hydrogel is even softer than the biological tissue, right? So it's soft and strong as well as the hard wall, right? So how about the fracture behavior? So this is very interesting. This is very interesting for the composite hydrogel. So here is a crack. When you cut a crack, the fibers will pull out gradually, right? So the crack can grow a little bit and then arrest. If you have a very large load, so the fiber will breaks and the crack propagates continuously. This is this direction. So in this vertical direction, the crack propagates only by cutting the fiber. So this direction has higher particular crack resistance. So we also carry out the FEM analysis simulation, right? So the two directions have different fracture behaviors. So, but if you want to make a good composite, you want the composite to resist the crack from multiple directions, right? You want it's tough in this direction, it's tough in this direction. So here, if you use a single layer fabric, the fatigue crack can also propagate. So here we use multi-layer fabric. So we laminate 2 layers of fabric, and you can see it can resist the fatigue crack. After 30,000 cycles, the fatigue crack does not grow anymore. So this material is very good. Its fatigue threshold is as good as the hard wall tissue. So now we have this soft material. We want to prepare or fabricate the hard wall using this composite hydrogel. Again, we use the suture thread to suture the leaflets of hydrogel onto the metal stent, and then we do the fatigue test using the pulsatile flow. We control the pressure gradient, right? So here, if you only have the PVA hydrogel, the fatigue life is low, it's 0.2 million cycles. So if you use our composite hydrogel, the fatigue life is very high. It's 25 million cycles, right? So the increment is very high. It's larger than 100 times. So we can see the fiber reinforced strategy is useful for the fatigue resistant hydrogels. Okay, so the final part. So the final part is about the applications in the hard wall. So previously we see the biological tissues like the bovine pericardium is very well, but it also has the drawback. The drawback is that it's very costly and it's prone to calcification. So what's calcification? The calcium ions in the blood will deposit on the heart valve. You can see the heart valve becomes very ugly, right? And its morphology changes a lot and it becomes very stiff. It's as stiff as a stone. So it cannot open and close well. So people always want to prepare the synthetic heart valve using the TPU leaflet or hydrogel, right? So the synthetic materials, what's the problem for synthetic material? The problem is that their fatigue resistance is very, very poor. It's very, very poor. So now our ongoing research is to design the polymer heart valves using the fiber reinforced composite, right? So we published 2 meta papers, but we still cannot reach the requirement. The requirement for the commercial product is at least 200 million cycles, the fatigue life. So now we are still doing this project. So for the PV hydrogel, as we see, the fatigue life is about 0.2 to 0.8 million cycles. So for the woven composite, the fatigue life is very good, but it's too stiff. So we use the knitted fiber. As we say, we use the knitted nylon fiber. it can reach 15 or 25 million cycles, but it's still one order of magnitude difference. So when we do this project, actually we carried out animal tests to evaluate the biocompatibility of this composite. Here, we use the sheep, right? We use sheep and pigs, and we use the gateware here. In this video, you can see we use the gateware to get the heart valve in the location of the heart, and this is the stent. This is the heart valve deployment process, right? So here is the animal. Here is the animal. Okay, we actually we do animal test of 1 sheep and 3 pigs. So the animal test is still on the way. So okay, to summarize. So in my talk, actually I introduce 4 parts. So we investigate the fatigue fracture of hydrogel, and we review the fatigue-resistant mechanism of soft tissues. So why the heart valve is so fatigue-resistant, right? And we use this fatigue-resistant mechanism to develop the fatigue-resistant hydrogels using the fiber-reinforced strategy. And finally, our final goal is to explore the application of these fatigue-resistant hydrogels in heart valve. So this is our conclusion. So finally, I want to thank my collaborator, Professor Zhigang Shuo, Professor Tiejun Wang, and this is the hospital doctor, Professor Yang Jian, and this is the company CEO for the biomedical company. And I want also thank my students. Okay, thanks. So, Mingchao, so that's my
okay. Yeah, thank you, Jinda, for very inspiring and wonderful talk. And he has introduced a wide range of topics, I think, from the materials, from the mechanism investigation to materials development, and finally gave us very inspiring examples of how those materials can be applied to real biomedical applications. This is very important. I think we can expect that once your materials has been used in the real human body, it will change our life quite a lot. So now I think it's time for question and discussions. So yeah, welcome to either raise your hand or just type your question in the chat. So is there any questions regarding to Jinda's talk? So yeah, we are still open for questions. So first of all, I would like to ask a question about your talk. Actually, I'm not a real material scientist, and I don't know too much about hydrogel either. So, but I quite interested in a general question about the materials development. Mostly we are interested in some materials we can change its properties. For example, we design a hydrogel or any other materials. It is intrinsically soft, but how can we make it to be tenable? For example, we want to change its stiffness or the fracture toughness once you've fabricated the materials. So do you have any comments about this kind of tenability or programmability for your hydrogel materials?
Okay, thank you, Mingzhao, for this good question. So the hydrogel, right? The hydrogel is this is the basic structure for the hydrogel. The hydrogel contains water and polymer, right? So for the
I sharing the screen.
Yes, can you see?
Now we are seeing your last page.
Okay, sorry. Here, okay. Okay, so here. Yeah, so the hydrogel is made of polymer network and the water molecules, right? This is the polymer network. So when you change there are many factors you can change. How like the polymer chain length, right? If you cross-link, this is the cross-link, this is the polymer chain. So if you put a lot of cross-link, so the polymer chain will becomes very short, so the modulus can be changed. And this is one polymer network. And then here, if you further, right, add another polymer network, this is a double network, and you can tune the toughness of the fatigue property. And so this is on the scale of the polymer chain. So now people are doing the composite, right? Like here. Right, this is here. If you for example, this page. So here you can use the matrix and the fiber, right? And the fiber to reinforce the matrix. So it's a kind of multi-skill material design strategy. So you can design it on the molecular level. You can design it as the macroscopic level, and it's a lot of space for you to design or program the mechanical properties for hydrogel.
Okay, yeah, it's great. Thank you. Is there any questions online? Okay, so if no, I would like to ask a further question about your application. So you are talking about you are going to you are using the those kind of hydrogel for biomedical applications. For example, you will put in to make the heart valve. So as we know, if the materials can be biodegradable, that would be really helpful. So, but basically, the biodegradable properties is somehow conflicts to the resistance of fatigue. Is that right?
Yes,
so,
yes.
Is there any good solutions to merge those two properties in one type of materials from your point of view?
Okay. So this is a very good question. So actually, we do not explore that part. So the biodegradable polymer you see, right? So for the hard valve case, so actually people do not want it to be biodegradable. So you want the hydrogel to be there for forever, right? Forever. So the biodegradable, right? So
yeah, for hot valve definitely it's not necessary to have biodegradable, but as because I'm not expert for hydrogel, but I know some papers or some works are talking about the applications of hydrogel in human body, and for some particular situations you may want to make it biodegradable, because for some cases you need to rather than biodegradable you need to take it out. Is that right?
yes. So
yeah,
yes.
so this is the reason I'm asking, but I understand it's not so relevant to your specific applications about the heart valve.
Yes. So actually, this is a good, very good research topic. So I think the fatigue property for these biodegradable materials will decrease. As the time goes by. Yeah, I think we can do it. We can do it in the future. Thank you, Minzhang. Yeah.
Great. Okay, so is there any other questions? So
there's questions from WeChat live streaming. Someone is asking, sorry, did you tested biological capacity for heart?
Okay. Yeah. So thank you for your question. Actually, in this in our ongoing research, so we have done the small animal test. We implant the material in the rat, in the mouse, and to evaluate the biocompatibility for this material. Actually, we are doing this research. It's the completely is very good.
Okay, so is there any further questions from WeChat?
No, that's the only one. That's all.
Okay, great. In that case, I think considering time, and I guess we can close the talk here today. And thank you all for joining this very interesting talk, and especially thanks Jinda for giving us this inspiring talk, and looking forward to your more interesting work in the future.
Thank you, Mingzong.
Okay, so yeah, I guess we can stop here.
Okay, thank you everyone. Bye.
Bye.